Hey guys, 2 weeks ago I presented a solution to IMO 2021 problem 2. Today I want to cover a variation of that problem where we remove the square roots from the summands on both sides. So we are asked to prove that the following inequality holds for all real x1 up to xn. So the double sum of I and j going from 1 to n of the absolute value of xi minus xj should be less than or equal to the same double sum of the absolute values of xi plus xj. The solution from the IMO problem actually exactly works for this one as well, but I want to present a solution that is easier to come up with, at least in my opinion. Since we sum over the same indices on the left and on the right side, it is of course a good idea to take everything on the right side, and then our inequality becomes that we are asked to prove that 0 is less than or equal to the double sum of I and j going from 1 to n of the absolute value of xi plus xj minus the absolute value of xi minus xj. This term reminds us of an equation which I want to notice, namely that x plus y minus the absolute value of x minus y is always equal to 2 times their minimum. And if you have never seen this equation before, it would still make sense to take a look at a term like that when encountering this summand, because here we have two absolute value terms and the absolute value function behaves weird in the sense that we have to consider different cases. So we could just say, let's ignore the first absolute values, then we would get something like that. And the reason why this is equal to 2 times the minimum of x and y is that if, for example, y is the minimum of x and y, then the absolute value of x minus y is just x minus y, and then of course we get 2y, and this also works the other way around. What we observe here is that if we know which of x and y is larger, then this equation becomes very easy. Similarly, we can take a look at our summands, and then of course if we also know which of xi and xj is larger, and if we know whether xi plus xj is positive or negative, then these summands are also very easy. This motivates us to take a look at the different cases for these inequality signs and take a look at which value this summand can take. So I wrote down all of the different cases for this value, and you can check for yourself that this is true. I actually think that this is a very good exercise. This is exactly what I did when trying to solve this problem. We now notice that in any case we only get some factor and then one of our variables, as it was the case in our easier example. This is of course very nice. And furthermore, if we take a look at our first line, we see that this condition here is exactly equivalent to x being at least the absolute value of y. Of course, this also works for the other cases. If we take a look at line 2, we can multiply the first inequality by -1, so we get minus x is less than or equal to y. So in total, all of this is equivalent to y is greater than or equal to the absolute value of x. And in the third and fourth case, we do analogous things. As is the case for the most part of the first step of our solution, we want to take a good look at these 4 cases and try to come up with a correct product term that is always equal to this. And we see that 2 times the minimum of the absolute value of x and the absolute value of y times signum of x times signum of y satisfies this. Here we define the signum or sign of x to be +1 if x is positive, -1 if x is negative, and 0 for x equal to 0. And we see that this is a really nice and symmetric term. We can plug this in to our original sum to get that all of this is equal to the sum of I and j going from 1 to n of 2 times the minimum of the absolute value of xi and xj times the signum of xi and the signum of xj. Now we can see why this reformulation is really useful. On the left side we have terms like the absolute value of xi plus xj. For different values of I and j, this takes around n squared different values, whereas on the right side, we are really only having terms of the form plus or minus 2 times the absolute value of xi or xj. So these are a lot less different sums. Furthermore, if we ignore this weight in front, this double sum is exactly the value for the sum of signum xi for I is equal to 1 up to n all squared. So we want to note this down. This is a square and therefore greater than or equal to 0, which finishes our proof for the case that all of the absolute values of xi are equal to some constant c greater than or equal to 0. Of course, we cannot assume that. So we have to deal with the case that the weights in front of the signum terms are not all equal. We can still use this identity. Because this is greater than or equal to 0, we can subtract this double sum from our original double sum to get a lower bound on it, and we can even multiply during that subtraction with some non-negative factor alpha. So let's write that down. So we get that all of this is greater than or equal to 2 times the sum of I and j going from 1 to n of the minimum of absolute value xi and absolute value xj minus some non-negative alpha times signum xi times signum xj. Now we want to make a suitable choice for alpha such that our problem simplifies. Note that many of those minimum of absolute value xi, absolute value xj terms are equal. Therefore, we can set alpha to be equal to one of those terms, namely absolute value of xi for some I, and then we're going to have many weights equal to 0. Furthermore, note that all of those weights are non-negative. Therefore, we would like to choose alpha in such a way that after subtracting it from all of the weights, we are going to be left with non-negative weights again. Thus, we want alpha to be the minimum of the absolute values of xi for all indices I. For convenience, we first assume, without loss of generality, that the absolute value of xn is actually minimal, so let xn, the absolute value of xn, be the minimum of the absolute value of xi for 1 less than or equal to I less than or equal to n. Now we set alpha to be the absolute value of xn, so let's plug this into our inequality. We can take the minus absolute value of xn into our minimum to get a similar term as in our first line, and therefore we obtain that all of this is equal to the double sum of I and j going from 1 to n of the minimum of absolute value xi minus absolute value xn and the absolute value of xj minus the absolute value of xn. And now we just multiply with signum xi and signum xj. Due to our choice of alpha, this minimum term is equal to 0 if I or j is already equal to n. And therefore we can ignore all of those terms, so all of this is equal to the same double sum, but for I and j going from 1 to n minus 1. This motivates us to try to use induction on the number of variables. Therefore, we would like to define new variables xi prime such that the absolute value of xi prime is exactly equal to the absolute value of xi minus absolute value xn, and such that the signum of xi prime is just equal to signum xi. Because the distance from 0 to xi is at least the absolute value of xn, by this we can see that all of this can be achieved by just moving xi by absolute value of xn units towards 0. Therefore, let us define xi prime to be equal to xi minus absolute value of xn times the sine of xi. For xi greater than 0, we get xi prime equal to xi minus absolute value of xn. Therefore, this is indeed going to be the absolute value of xi prime. Furthermore, by this assumption, xi is going to be greater than or equal to the absolute value of xn. If it is greater than absolute value of xn, then the sine of xi prime is again going to be equal to 1, which will equal sine of xi, which is what we want. And then there's an edge case where xi is indeed equal to the absolute value of xn. Then we're going to have sine of xi prime is equal to 0, which is not sine of xi. But in that case, the absolute value of xi prime is also 0, so that doesn't make any difference. We get the same thing for xi less than 0. Lastly, we have to deal with xi equal to 0, but then, due to this assumption, we are also going to have absolute value of xn equal to 0, and therefore all of the xi primes are just going to be the xi's, and so in that case the equality is going to be trivial. And thus, in any case, we get that all of this is equal to 2 times the double sum of I and j going from 1 to n minus 1 of the minimum of absolute value xi prime and absolute value xj prime times sine xi prime sine xj prime. This is the point where I have to note that this just works for n greater than or equal to 1. But we want to use induction, which works perfectly here, because we know that for n is equal to 0, we just get that this inequality is 0 less than or equal to 0, which is fine. So we can start an induction, and if we assume that for n greater than or equal to 1, the inequality holds for n minus 1, then this is all going to be greater than or equal to 0, and therefore, by induction, we know that the inequality holds for all natural numbers n, and therefore we are done.